Okay, there we go. Alrighty. So we're gonna actually get going today with transformers. So this is kind of an extension of sequence-to-sequence models and attention within recurrent neural nets. But now we're gonna actually get into the main meat of it, where it turns out you don't need any of the other fluff, and we're just going to use attention mechanisms throughout the entire architecture. Okay, so from some of the models we looked at, we saw that we had an encoding part of the network and a decoding part of the network, and then some communication mechanism between the two parts, right? And so what we've seen already is that the encoder can be an RNN or a CNN. It's something that takes in the context. It doesn't have to produce an output, but it just has to summarize and get some kind of summary vector at the end of its process for the entire sentence string that it's been given. Okay. Similarly, the decoder, from what we could see, it was just incorporating new information, keeping track of what had already been said on top of kind of trying to keep the information passed in from the encoder. And then finally, we got to this point where we said, well, the encoder has this problem where it has to always try and compress all of the same information into a fixed size vector. So that was the encoding problem. And then the decoding problem was that the decoder wanted different information from that vector at different times. And so having just one stable representation for that wasn't that useful. We wanted to try and prioritize certain information. And that's where we brought in this idea of attention. And we had this third mechanism where, based on what the decoder was doing, we were going to then extract different information from the encoder and pass it along. All right. And so that was this third stream of information that we saw. Okay. And so we've seen some versions of this. Sometimes it's just fixed and the recurrence keeps rolling out. But then obviously we got to the more sophisticated version, which was then those like early models by Buttonu, for example, which incorporated cross attention. Now, as it was actually preempted by a question a few weeks ago, we're going to get to the transformer architecture, which says, hey, maybe I can just completely ignore RNNs because they have this fixed size structure, and they have to kind of compress everything into a single vector. Maybe I can just do attention at all pieces of my architecture. The encoder is going to be based on attention, the decoder on attention, and then the cross communication. And that got to the name of the paper. Attention is all you need. In other words, you don't need recurrence. You don't need convolution. You just needed this kind of one mechanism across all of your pieces. Okay. So the idea here is that you can try and now break down like who is doing what and what they're doing. So let's look at the encoder. So the encoder is going to look at all source tokens, and what they're going to try and do is update the representations of each of the tokens that they're getting in from the context based on the other words. And this is very much the same idea as like a word to vec, where you want to disambiguate words based on the other words they're surrounded by, right? So for example, if I've just read in the token for bank, where with my encoder model or encoder part of the model, then what I'm going to do is I'm going to say, well, I don't quite understand how to encode that, right? Like I can tokenize it, I can put that into some kind of embedding space as its own word, but that word now has multiple semantics because it might be a financial bank, it might be the river bank, and so on. And so if I look just at that embedding for bank, it's going to be quite imprecise. It's going to be overly general because it needs to accommodate all uses of the word bank. So what am I going to do? Well, I'm going to look at the other words in my sentence to try and see which version of bank am I actually talking about at the moment, and then update that token representation to be more specific. And then on top of that, I'm going to do this repeatedly. So I'm going to constantly, as I go deeper in these layers, and we'll look at it a little bit more concretely in a second, as I go deeper in these attention layers, I'm going to update my tokens more and more based on the surrounding words in the surrounding context. Because, for example, now at the second layer, I have an embedding representation for the word bank, but it's been disambiguated. I now know that we're talking about the financial bank, which then helps me disambiguate other words. All right. And so this addition of context and this incorporation of context as you go deeper and deeper allows for some pretty sophisticated mechanisms to emerge. And one of them that we're going to actually see in a few weeks when we get to like our last lecture, the kind of high level modern lecture, is called an induction head. And what that is where one attention mechanism looks back in the context, and then a second layer allows you to then do a look forward and a copy. All right. So they can stack, and it turns out in the kind of more recent views of transformers, that's a really big direction of research, is trying to understand how stacks of attention layers form little integral pieces of work that you can't just do with one of the mechanisms. And in that case, that's called a circuit. But again, we'll come to that. On the decoder side, you're going to take in the target token at the current step. And again, you're going to now be looking at all the previous tokens on that you've seen, so all the previous tokens you generated, but you're also going to be attending back to the source representations, and you're going to be trying to update the representations for a word based on all of the previous context, right? And again, we're going to have depth in this architecture to do the same thing. So here's the example that we've already made. I arrived at the bank after crossing the street or river. You don't know in this case what bank means in the sentence, and so you need to kind of try and find other information. So the RNN would say, I have no idea. Let's wait until I read until the end. So now I have to go through the entire sentence, okay, before I can now try and start disambiguating that word bank. All right. So I have to get to the point where I see the word street or river before I can kind of start to say what I'm talking about. And so this takes order n steps to process the sentence, if that's length n. And so the problem is RNNs have to do this sequentially. Whereas a transformer, this happens in constant time, right? Because the mechanism for attention is highly, highly parallelizable. So for every single token that I am reading in, I will do self-attention to all the other tokens, okay? Update my information, and then propagate it forward to the next layer. What it didn't wait for was any sort of rollout or sequential processing before I could update any one of those tokens on the encoder. And this is, in truth, the main revolution of transformers, right? There's a lot of open questions about why they work and how they work and whether or not it's low rank in the attention module and all of those things. But ultimately, what made them really, really effective was the fact that they were highly parallelizable, which meant we could throw more data at it, which meant they scaled better. Okay, data then ended up becoming the kind of primary resource. As you all know, we're now building server centers in the US to kind of burn down the world. But that's the scale that we're now at. The architecture will accommodate as much information as we want to throw at it. And so now it's just a case of let's get more information and see what happens. And then that led to some really cool discoveries, like with the fact that if you throw more words at it, it just gets better. These are called neural scaling rules. Again, it's something we'll chat about very briefly. But it turns out transformers, given the parallelization of their training, means that they scale very well in practice. Okay? And so that's the nice thing about transformers, is that you can disambiguate the word bank in that sentence almost instantly with order 1 computation. So that's the main idea. And let's now start digging into how this is actually going to go. Okay, so why do we call it self-attention? All right. So a decoder encoder attention is looking from obviously one decoder state across to all the encoder states. Now for self-attention, what we're going to have is for each state from a set of states, they're going to look at all the other states in the same set, right? Now, so I know that sounds wordy, but essentially the set of states here, all right, is just your input tokens in the encoder or input tokens in the decoder. So it's self-attention because now your encoder attends to itself, all right? Decoder attends to itself. Whereas previously what we saw with our sequence-to-sequence models was you only had decoder to encoder attention. Okay? And so in practice, this happens all in parallel, but let's say I am reading in a... Sorry. All right. Okay, so what we're going to do here is, let's say we are now reading in all of our tokens at once, right? And we're doing, again, sequence-to-sequence task. In this case, it doesn't have the encoder-decoder architecture. We're just going to do it like this for now. Okay, so what this is going to say is the same process we saw previously, where we're going to take in a token. You're going to now attend to all of the others. And again, we saw a whole bunch of different computations that can be used for attention. You could throw it into a neural network or whatever. But in our case, it actually ended up being a little bit more simple, I guess, or kind of intuitive or straightforward with how a machine learning idea of it would go. But anyway, you can abstract that away for now. All we do is you take some embedding representation for the word I'm currently looking at, and you do a computation with all of the other embeddings in the same set, or in other words, in the same encoder or decoder. All right, that then gives you a softmax. Okay, we know that softmax then turns propensities, the output from the attention mechanism, into a probability distribution, or at least something that when it sums up, it sums to 1, which means we can do a linear interpolation. Okay, and so these become the weights that are used to multiply all of these other token embeddings, and then that gets added back into our updated embedding. All right, so you gather information from your context, and then you update each token representation. And as you can see, there is not a single sideways arrow in any of these diagrams here. All right, so if I'm processing the word, backwards R or I or whatever, then I do not have to know anything about the other words, or I do not have to process information forward to any of the other words before I am able to update that first token. All right, and so ultimately you can do all of this completely in parallel. Okay, and so the mechanism that we actually use for this is the following, and this is one of the more important slides in the class. So keep, if you focus, this is probably the next 10 minutes that you want to focus on. So also what I will say is if you read the attention is all you need paper, this to me doesn't come through super clearly. That's actually why I like these slides. So yeah, if you read the paper, just keep your wits about you. That notation gets a little bit fuzzy and actually does trickle through to some of these later slides. So what's going to happen is each vector receives 3 representations, right? It has 3 roles. It has the query, the key, and the value. All right. For the word we are currently looking at, we are going to produce a query. Okay. That vector, that query vector says, this is the information I should go looking for. In other words, that will be useful. Okay. It is learned by a linear mapping. All right. So you take your green vector over here, green vector over there, and you multiply it by a weight matrix WQ. All right. This is the vector from which the attention is going to be looking. So it's essentially saying, hey, what information, or do you have this information to the other embeddings? Okay, then every other embedding on the same side, or in kind of the in the architecture, so in this case the encoder, will then be given 2 other vectors. The first is a key. Same idea as the query. All right, we're going to learn that by multiplying it just with a matrix multiplication. It's also going to be a square matrix multiplication so that you can always do these, that you're not like losing dimensions, right? We know that we're ultimately going to have to multiply these vectors somewhere. All right, so you propagate it forward, and now your query and your key vectors are the same dimension, which means that they can be dot producted later on. Okay, so now we have a vector that says, the query vector, the blue one, that says, what information do I need? And we have a key saying, what information does this token have? All right, so it's the vector at which the query looks to compute weights, and it's a kind of a representation of what information this token down here might have that can be used to disambiguate the ones next to it. All right, and then lastly, you get your value, which is then the weighted sum of the attention output, and then so that is ultimately the information that gets propagated forward. Same idea. You're going to take the input embedding, map it forward into a vector, and then the value is what gets, you can see the value is what gets propagated forward over there. Okay, so the query and the key, the blue and the yellow, filter into our attention mechanism over here. All right, you can see those 2 pathways over there. Let me find a better color for this. Okay, so we have those 2 pieces of information propagating forward there. They then give us our attention weights, all right, the little dot as with the previous diagrams that we looked at. And then from there, that information is now propagated forward and used to determine how much of the red information gets kind of used to update the representation, all right? And so it ends up becoming a linear sum of your value, a linear combination of your value vectors, and then that gets used to update the vector representation. Right, we'll see it now in a little bit more notation, but it is important just to keep note of which pieces go together, right? The key and the query are there only to give us what to look at, all right? And that's what's nice about the fact that these are three different weight matrices over there, is because they can do entirely different jobs on the green embedding vectors, right? The query can map one word into one space. The key will map another word into the same space so that when we dot product them, when we do our attention mechanism, there is a high response, all right? And that's the kind of whole idea, is that these different token embeddings get related through the different matrices that we're learning. All right. As you can all imagine, the next step to this is to say, well, maybe I want to do that lots of times. Maybe having one relation is not enough. Maybe learning one set of relations is not enough. And in which case, we're going to do more of these, and you would be exactly right. Okay. But let's now focus in on the attention mechanism. What is actually going on? Well, firstly, we're going to multiply the query vector with our key vector. All right. I don't like the notation here because it transposes this to get it to be a column. And we all know if you took MFDS that columns are vectors and rows are not. But anyway, we'll forgive the notation. The query gets multiplied with the key so that we're able to get a scalar value out over here at the bottom. That then gives us our attention weight for this embedding here. Okay, this is specifically the attention weight for the embedding for cat. All right, so this is going to be adaptive. Every single time I do this, it's going to give me a different weight, depending on whether or not the word I is relevant to cat or relevant to the word mat will determine the weight that is given out the back of this. Okay, the last thing to note is you'll see that there is this divide by dk. All right, so that's the dimensions of our key embedding. All right, so that's the dimensions of this vector here. The reason for that is, and you can kind of prove this, we're not going to, but the reason for this is so that these vectors all stay within a roughly normalized range, and so that your softmax ends up becoming stable. All right, it essentially works like a temperature on that softmax that they have found works really, really well. And the reason it works really, really well, and again, there's deeper things to this architecture we'll see in a second, is because every time I pass these tokens into an into an attention layer, they have a specific scale. All right, there's some more mechanisms that are always trying to normalize the amount of information that is being passed in. And so in that case, we know quite well how to set the temperature on the softmax. All right. So it's an implementation detail. Again, these were things that kind of got found somewhat over time and were, essentially hand wavy to begin with before people start to realize the benefits of it. And now there are actually many, many people that believe that square root by dk, that vector dimensionality, is actually doing a lot of heavy lifting. All right. The fact that the weights are normalized, these attention weights are normalized in a specific way, they actually think that is diffusing the attention well, so that transformers don't succumb to all the usual problems that they have. All right. So again, it's not the first thing you learn about transformer, but something to keep in mind that attention mechanism has a very specific temperature in your softmax. Okay. Anyway, then we get what is called our attention weights. All right. So if in a test I ever asked you to get the attention matrix or the attention weights, you're going to give me that. That is A. You will not give me the whole thing. All right. Hint, hint, that's what everyone does wrong every single year. You don't lose marks on it. You just waste, 10 minutes of your life now doing matrix multiplication to get V. If we want attention, the attention piece of the network is only this. Okay, those are called our attention weights or attention weightings. Okay, that gives us a scalar that says how relevant this token was to the one I'm currently trying to update. All right. That is what this scalar is here, and it then gets used to multiply the value vector for that word up there, right? You notice that the cat, the word I'm updating, doesn't have a value vector, all right? It's not being used anywhere in this forward pass to get the red vector. That should already be saying that's a bit weird, all right? And if you're already thinking that that's a bit strange, you're on track, because there is another way that we incorporate the information in a second, okay? So all we're doing now is building out this weighted sum of value vectors, all right, where these values is just a linear mapping off of our tokens, and then the weighted sum is given to us by the attention mechanism. All right, I know I'm probably going through this slowly or laboring on it, but this is intricate and important. All right. Is everyone up to scratch so far? Are we happy? Are we seeing the flow of information through the network? We good? You don't look convinced. It makes sense? Guys online, are we happy? Anyone got any questions or reasons for me to stop? Sure. So looking at this image here, which word has the highest attention weight for cat? Correct. It's just that bar coming off the top of the softmax. Right. And if I went A, B, C, D, E, which value vector is being used to update the embedding for cat based on the word saw? Should I say it again? What's that? Correct. There we go. Okay, that's correct, right? So again, just to recap, we're trying to update the embedding for one of the words at the moment. It's called cat. Okay, we're going to compute a key vector, which is the blue vector. All right, that is a vector that is able to find other information in different tokens. Okay, then for every other token, not the one for cat, every other token, we're going to make a query vector. Okay, that's the yellow K in notation. Okay, keys and queries go together. When we get the dot product and those vectors are pointing in the same direction, as we know, that's how dot product, what maximizes the dot product, right? When vectors point in the same direction, they will be high. When they point in different directions or they're orthogonal, that will be low, right? In this case, if they point in the opposite directions, it's going to be negative, which means that that's going to go into a softmax, and the softmax is going to reduce that. So ultimately, all we really want is these two vectors to point in the same way. It's why something like cosine similarity is used a lot in interpreting these neural networks in transformers. Okay, and it goes together just like I guess, kind of like a lock and a key, right? Your query is the key, and then your key is the key, and your query is like the lock, right? You just put them together, and they are responsive if they match. Okay, if they match, that means that this mechanism here will put a high value on them relative to the others, right? They're competing for attention, and the competition comes from the softmax. We know that when one value is really large over here, that will push down all of the others inside of the softmax, because you always divide by the sum of the activity. Okay? So this is really where that name attention comes from. It's the fact that it is a competitive limited resource. Okay, and this is also where a lot of the weird behaviors apparently are coming from. And I think very recently they're starting to see that hallucinations have an effect. It's due to how the softmax is collapsing in certain cases. All right, but again, we know that that's largely why that should be there. So there are some failure modes. All right, so what do? We take our key and we multiply it with all the other queries. That tells us how relevant all the other tokens are to the word I'm trying to update. All right. I divide by this fancy little, nice temperature term so that my softmax behaves nicely. And then I run it through a softmax. They compete for my attention. And then that gives me a weighting on how much I should care about these other words in the sentence when I'm trying to update the word cat. Okay, that gives me my linear weightings. And then after that, all I do is take this value vector, which is its own thing. It's its own little, skip forward, right? It gets generated in its own right from from the embedding. Okay, so from, I guess that's end of sentence. Let's not be dumb. From the word saw, all right? I take the embedding, I map it forward, I get that value vector. So that now says, hey, if the word saw is relevant to the word cat, if attention is putting a lot of weight on this, then this is the information that you should want from that. All right. Like, hey, you found me, the key query matched. Now this is what I have to say about this. And then you propagate that forward, you multiply it by its weighting, and then it gets a weighted sum from there. Okay. And so your updated embedding over here is now the weighted sum of the value vectors from all the other token embeddings. Okay. And that is how self-attention works in a neural net. Any final questions before I move on? Yeah.
That values on the high response that gets so like in this case, yeah, it would be so always be one of the values.
The updated embedding is all of the values being added together, right? But they're added together with weightings based on the attention. So let's call this matrix, or let's call this, A1, A2, A3, right? And that's how much that's how much attention is being placed on the other words when I'm updating cat, right? So let's say this is A1, not do that, off the softmax. This is A1, this is A2, this is A3, A4, and A5, right? So those are the different weights coming out of my softmax for this competed attention. On top of that, we have our vectors, which is V1, V2, V3, V4, V5. This vector here is, let's just do the color. That's A1 plus A2 plus A3, so on. V1, V2, V3, so on. Okay, so you get the attention weight that A is only coming from my key query. Okay, this but here is just the key query thing to get A with the softmax included is there. And then those give me just scalar values to multiply my values with.
So the like part of that is that V.
It's the sum of all the V's.
Yeah. So yeah.
Oh, I see what you're saying. Yes, they've written it in vector form. Yes, correct.
That is just that's half the weight.
No. This is not V here. This is all of these different V's, so that when I do this dot product, I get this here. There. It's the product of all the V's. They've just stacked it in the notation into different vectors. All right. So that is self-attention. Okay, so that is largely what's going to how this information is going to flow, but that looks at at an encoder side, right? That relied on me being given all of the tokens at once. That is not going to happen in language modeling, right? We know that we produce one word at a time, at least in this case, and so this is only going to work this way for an encoder when I'm given my context and I need to encode it and update that encoding over here. Note that while it's using these English words up top here, what we haven't done is translation. All I've done is updated the token representation for kato up top here. They're just using the word cat there to make sure you see it. Okay, the encoder in the attention is not going to do so. It's not going to produce words. We will come to that, and that is the decoder. So now on the decoder, we use what's called masked self-attention, right? So it's one small caveat on top of self-attention. We're still going to be looking at all the other tokens, but I'm just not going to let the words look forward in the sentence, okay? Even if I am going to give you that information, right? When we're training, obviously when we train, we have that information. We know what the output sentence should be in our sequence-to-sequence model. The problem is we can't give that to the transformer because then when I want to deploy it, when ChatGPT needs to start actually speaking to me, it doesn't have that information yet. It doesn't know what it's going to say in the future. It hasn't decoded those words yet. So you essentially just need to train your transformer to never know the future in its decoder, right? So in the decoder, we forbid it for looking at future tokens because we don't know them when we actually deploy it. In training, the decoder processes all tokens at once without masks. If it processes without masks, it would see the future. Okay, so we obviously can't do that. So you stop it, right? In any case where it could be looking to the future, you would just zero out that element going into the softmax. As a result, it doesn't affect the softmax. Now you don't get a sum over zeros. And then you end up just putting weights on what is previously there and then training so that you can do the same mechanism going forward, just without the benefit of the future tokens. Okay, so in this case now, you were looking at one word. There's only one word to attend to. So you would update it only with its value and only get its value vector. And then that's what gets propagated forward. Okay, at that point, what have you done? All right, well, obviously your keys and queries, there was one of them. So softmax ended up going to 1. All right, so you put all your weight on the one word in the decoder already. What does that mean? Well, if we look at this over here, the output of your softmax is 1. You have a single value vector. And so that means that we've actually just propagated one bit of information, which is the one word we had, times its linear mapping over there. So in that case, it just collapsed back down to a normal deep neural network. Just a single layer matrix multiplication to propagate that information forward is all it could muster, but that's good. That means when there's one word to attend to, it just becomes a neural network, which we know work well, right? They've been the standard for other things for many, many years. And so at least it collapses onto something we think should be reasonable for now. When I start adding other words in, then I can start updating more information, kind of actually, using the attention mechanism to its full power. But this is an important point, is the transformer never had any mechanism in it that would allow for a clear failure. In any case where you didn't have the information you wanted, or you had one thing being passed into the softmax, it would collapse onto something reasonable, like just a feed-forward neural network. Okay, so that's another big reason why transformer worked. It was parallelizable, and it had fairly stable computation that returned to something else when it wasn't working. It would just collapse onto a neural net, a deep neural net. Okay, do we all understand masked self-attention? You're right. You just zero out the attention weights for future tokens. Okay. All right. This is where the complexity starts ramping up a little bit. So if you do have any questions, now is a good time to stop me. Okay. We'll keep going. So now, as I said, there are multiple things you want to track while you're processing a sentence, right? It's not just about looking for, what the cat, or whether or not saw and cat were relevant, for example, in that previous example. We want to have many things, right? You want to look back in your text for names. You want to look back in the text for gender agreement. You want to look for lexical preferences. You want to go back and look through all bunch of information that came through in that sentence, right? So one attention mechanism isn't going to be enough to find multiple relationships between words. And so what we actually have to do is just have multiple of them, all right? And so it is genuinely that idea. So if you understand self-attention and you understand the masked self-attention, then this should fall out pretty straightforward. All we're going to do is do multiple of them, okay? So again, you feed in your words into an attention mechanism, right? We have our embeddings at the bottom. And in blue is the output of that first block of attention, all right? And you get the weighted sums, those little histograms off of our softmax. And then those are the weightings on the values, okay? So I know we've abstracted away a few things. We're not now showing you the keys and the queries and the values, but that is the mechanism that's being used to propagate information forward over here. One thing to note is while we did have that D of K notation earlier, all right, and we were square rooting it, D of K was the dimension of our key, and by implicitly also the dimension of our query, because they had to be dot producted, all right? What we can do, though, is have a different dimension for our value vector, because that is just a scaling, right? That's just a, in reality, that is just taking in these linear scales and then being added together at the top there, right? So you can have different value vectors as an intermediate step, right? The problem with that is that then it becomes hard to stack them and things like that. So in almost all cases, you keep V the same dimension as the dimension of your input embeddings. But now when we're doing self-attention or multi-header self-attention, right, we're going to decrease the size of the value vectors, okay? But then we're going to have more of them, and we're going to start stacking that output of the value vectors, right? So now in purple, this is an entirely different attention head, okay? That's what they're called. So what does that mean? This is an entirely different set of WQ, WK, and WV, all right? Doing its own bit of computation, giving you a different query, giving you a different key for all of the other tokens, and then propagating different information forward through the value vector. All right, all doing different things. And as you can see, they all work independently. And so we'll have multiple of them, and we just keep stacking them together. And eventually, that gives us this concatenation of all of the values. All right. From there, you can then do another mapping down onto the same dimension as what was fed in. All right. So we had 3 dimensions coming in. We know we want 3 dimensions coming out so that we can stack these things. And so now you then have to output back to a 3-dimensional layer. All right. And that is usually done with this just dense linear mapping going forward. All right. So there's no guarantee that our values vector had to be a certain dimension. You make it slightly smaller because you know you're going to concatenate them. And then you just map forward onto the desired embedding size afterwards. And now that is the embedding that gets propagated forward over there. All right. Does everyone feel comfortable with this? Should I go through it again? Yeah. Yeah.
That's the same.
The output dimension of it, yes. Yeah, and then obviously the input size to that layer is the size of your values times by the number of attention heads. Okay, so again, to recap what we just did, we know how self-attention works. So now all we're going to do is just do a whole bunch of them. All right, multiple self-attentions with multiple weight matrices, WQ, WK, WV. They all give you new outputs after their softmax and their linear sum of the their weighted sum of the value vectors and all that. They all give you different outputs. So we're just going to concatenate them. We don't want to add. We don't want to do anything smarter than that. We're just going to concatenate because we want the network to know that that's coming from different information. It's coming from different attention heads. And so you shouldn't start to treat these values as conflatable or mixtures or anything like that. From there, we now have a vector representation that's too large. So we need to compress it. I don't know how to compress this embedding. I don't think anyone does. But I'm hoping that if I just do a mapping down to the desired dimensions and show it heaps and heaps of data, my neural network, gradient descent, and a little bit of magic will then give me the W that does a decent job of that. Okay. So you can represent it in notation. Again, I think this notation gets a little bit wobbly even when I look at it. But essentially what it's just trying to say is that you are taking the concatenation of all of these little attention heads over here and multiplying it by another weight matrix W0 or WO, all right? Your output weight matrix. Okay, where one individual head is operating on your token embeddings times by their own weight matrices. WI is over there for the ith attention head. Okay, so that's the important bit about that notation there is this little superscript I. Okay, what I don't like is the way they represent Q, K, and V here because those are actually still your embeddings at the bottom. But anyway, it makes a little bit more sense when you read the paper. And so the last thing to note is that, again, this is highly, highly parallelizable, all right? And so you can end up actually stacking these token embeddings coming on your input. You stack them, and you can do this mechanism in one forward pass. So you can do all of your multi-head attentions across the different heads by stacking them and then doing the same matrix multiplication over and over. And again, the nice thing about that is I'm no longer reusing matrix multiplications. I'm not now doing it one at a time. There's nothing sequential about this. I can do my full multi-head attention in a single forward pass. All right. The exact computational mechanism and the concatenating stuff is kind of details, I guess, but that's the key point to take away here. This mechanism, this multi-head attention mechanism, what it's doing is depicted on the right, and then the stuff on the left is saying it goes really, really efficiently. I can do it all in parallel, given a good enough GPU and enough memory to fit all of this on. Okay, and again, that, in my opinion, and in most people's opinion, is where the real power comes from, the parallelizability of these architectures. And again, when you do your project, you'll see this a little bit more concretely. All right. Is everyone happy so far? Yeah.
A really long sentence, but with all of that information, I think agenda.
You mean this mapping here?
Yeah.
Yeah, I mean, to a degree, right? But the difference here is that it's more adaptive still. So I agree with you, you're trying to represent a lot of information all at once. But these weight matrices coming out of the softmax, they're going to be small for most of them, right? You're only promoting a few tokens, which means that actually each individual vector here, like each individual output head, is really doing one thing very specifically, right? It doesn't have a ton of information in its own right. And so this vector that you've just concatenated here, number one, there's likely some redundancy in it. But number two, as much as I agree with you, it is a big vector. If you look at kind of how that vector is embedded in space, it's quite sparse. And in general, it's probably quite low rank, would be the mathematical way of saying it, in which case it can be effectively compressed. But I agree with you. If you're in a case where there's a lot of information being propagated forward and you have a really long sentence and all those things, there is still a case of a compression happening. But at least it's not a compression over my entire sentence. It's promoted. It's information that's being promoted by the current word. It is at least specific to what I'm doing. Good job. Good question. Anybody else? Guys online, are we there? Boom. All right. I think let's actually take a break there for 15 minutes and then we'll come back and talk about the full architecture. Yes. No. No, there's no max poolings. I mean, there's some other mechanisms inside this architecture here, which I'll speak about now. But if you're just talking about multi-head attention as we did it, there is no poolings and stuff. Yeah. So, I mean, each of these sums of the values, right, is going to represent its own information. Okay, so we're happy with that. We concatenate it, which then just says that, treat those dimensions as different things, right? They're all telling you different things about your data. Okay, and then you compress it down with a linear mapping. All right, so there's the competition for information happens at the level of the softmax. You know what I'm saying? But it's not max pooling, it's soft max pooling in a sense. But the important thing is that only gives you the weights as well, the attention weights. That's then what gives you that like linear combination of value vectors. what I'm saying? So it's not the same as in like a convolution where I say, where did my convolution, where was it most active? And I'm just going to return the most like activity that I saw anywhere in my sentence. It's certainly not that. It's a lot more parameterized in the sense that, that is something that now needs to be learned from data. These weights are something that need to be learned from data, all the keys, the queries, the values, and stuff like that.
No problem. When you said, and then we might need to get to like I guess when you do, market level, bottom coders, components, the happiness, then next to sort of respectful function that gets you there. Well, when living is a text from this, I didn't mention to us about.
So it's just a matrix multiplication.
I just don't know matrix multiplication.
Yeah, exactly. It's just so like, let's say that let's call this, notation's overloaded. Let's use B for that vector, right? Then all this is B times W0 is equal to, V star. So this is V star. Right. So it's just that linear mapping is over there.
I see.
All right. So
Just standard.
just vanilla linear mapping. Yeah, exactly. And that's like where this fallback to a linear network comes from, right? It's got the same pieces in there. It's just got a little bit of like a weighted sum in between.
Okay.
I'm just watching my stuff for 2 seconds. No. How was the test last week? You guys all happy with the questions and stuff? Yeah. What about it? Okay, we can go through that. I don't have that ready now, so. I suppose.
When you review, put it done correctly, what it's supposed to be.
Oh, I see. Okay, well, let me see. There might also be an incorrect answer. How do I do this without sharing this to everyone on Earth? All right. Guys online, can you see the screen, the Moodle page?
I see the slides.
You say wait, you can't see Moodle.
Yeah, I can only see the slides right now.
Okay, yeah. You can see it now, yeah?
Yes, I can.
Cool. All right, so yeah, this is at least what I had. Might be wrong, but let's see. Which of the following are true about language models when using an RNN as a language model initializing? The initial hidden state with random values rather than zeros can help the model generate more varied sentences. That's true. Any disputes? Right, so if you're going to pass in zeros, your information is going to then just be based on the beginning of sentence token, right? So you're always going to predict the same word. So you need to have, because you want to generate sentences, you need to have a little bit of randomness at the start to prime creativity, essentially. Then a large problem with using CNNs as language models is that they need to repeatedly process the same input words each time they generate a new word, making them inefficient. That is just true, right? Like you just have to keep rerunning the same convolutions over and over. Then CNNs cannot be used as language models as they are not recurrent. That's obviously false. They can generate new words. It's the same as doing text classification. It's just over your dictionary size. It just sucks because you have to redo convolution. Then D, language models are not conditioned on any additional information aside from what text has already been generated. That's not true, or not conditioned on anything about that. Yeah, no, that is true, right? Because it's sequence to sequence if you do it off that. So a language model just generates language. It doesn't actually take in a context. Right, so that is true. Then bidirectional RNNs are useful as language models since it means that the sentence is generated from left to right and from right to left simultaneously. Then the two generations meet in the middle, forming a coherent sentence. I was proud of that one. That's obviously false because you're not generating left to right, right to left. You're reading the sentence left to right, right to left to get to the embedding, but you still generate word after word. Using subword tokenization for language models can be useful as it means the model can produce new words by combining scene tokens. Whether it will ever need to is a different story. So yeah, subword tokenization is great. We looked at BPE and we said that the reason for that is because you don't have a fixed dictionary size. The technical term for it is you have an open dictionary. Okay, then if you train a language model without the softmax function at the end while still using cross entropy loss, the model will learn a more diverse latent space. That's just nonsense. And then it is impossible to create a language model that uses tokens which are smaller than words, for example, character level tokenizers. And it is possible to do this. They exist. You just don't always. BPE starts there though, and if BPE wanted to, it could. Any disputes? Which ones are weird? Why are you guys smiling at me? Which one was nasty? Which one should I not ask again? Like, what should I not do in the next quiz? You think it's fine? Cool.
Then they try and make it like combining to meaning like be there. You know what I mean?
Yeah. I mean,
It's kind of bad.
but you can still, yeah, I get what you're saying, but the point is that you can still tokenize and like embed that, right? You might not, and again, we see that it does do this. Like words like happy and un can be combined later in deeper layers to work properly, and they can kind of be tokenized like that. So again, when I get the word unhappy, it will tokenize as un, it will tokenize as happy. Both will be embedded appropriately, and then it's on the depth in that layer to try and combine that information. That's kind of what BPE is going to do. The new word will never, in BPE at least, the new word will never be tokenized as its own unit because you haven't seen that, right? It'll go look down that dictionary of scene tokens and try and find them inside of it. Admittedly, these questions are designed in this way, right? To make you question those things. So it takes longer than you'd expect to set a quiz like this. You gotta like try and kind of make sure that there's also sometimes, not all questions, there's a parsing difficulty to it as well, so that I can test that you actually understand what's going on. Or else, as you'll see, the distribution is just way too skewed. So I think what the average was close to 80% or something. Cool. All right, if there's no other questions about the quiz or anything, or no other points, we can carry on. Cool. Alrighty, so let's look at the full transformer architecture now. Okay, so you'll notice a couple of different things. Number one, you have inputs and then the outputs. It says shifted right. Okay, so that is to say that that's taking in the words that you have previously generated, right? So exactly as you would have seen a sequence-to-sequence model in the past, same story here, right? You're taking in the information you've already generated. It's shifted right from the output. Why? Because in the output, you're going to be producing the word cat, and that's your first word, whereas on the input, it's BOS token, then cat. It is shifted one to the right. Okay, so that's that. Then we have what are called positional embeddings. I will speak about position embeddings now. They are by far the trickiest points of this whole thing. And in general, they've also not used in the way that the original paper did it. But the way it did this is actually pretty sophisticated and cool. So we'll talk about it in a second. But you get some kind of a position embedding. Now, this is important. Transformers are permutation invariants. All right. We've seen one other kind of invariance equivariance before. That's convolutions. I could translate things in my input. I could move the picture of my cat from the top left to the top right of the image, and the convolution will respond the same, right? The output of the layer will be shifted. So in that case, it's equivariant. And then after the max pooling, it's just going to say, where did I find a cat in the image? I don't care about where. And then it becomes invariant. So in convolutions, I can move things around my input. In transformers, because this is all parallelizable over here, because it's all parallelizable, and we're doing the lookup between all other words and the focal word at all points in time in parallel, this means that I can swap these words here. And the output of my network, of this attention layer, will be identical. Why? Because when I swap those two words, their attention weights will also swap. But at the end of the day, I am then just going to use the same values coming in from those weightings. And so that linear sum at the end of my attention head stays exactly the same. All right. The place where the attention is sitting might move, but I still get the same attention weight, and I still get the same value vector being mapped off of that token. Okay. And so I can permute the words on my input sentence, swap their ordering. Okay. This is a big problem. Why? Because we know that words ordering in the sentence matter at the very minimum in terms of grammar, right? We know that we have subject, verb, object as like a base of the way language is created, right? At least in, English and those kinds of languages, right? So we now know that we need word order. That matters. So the fact that I've lost word order really could change the sentence, all right? The fact that Devin loves cats and cats love Devin are two very different things, and one may be more true than the other, right? And so now there's a problem that if I'm not being able to disambiguate those things, I'm going to lose information. I'm going to do the things that are wrong. Okay. So we have what's called position embeddings, right? That tell me that no, Devin was the first word in my sentence. It wasn't the third. And therefore there is now still some kind of order going into our representations. Okay. From there, let's look at the encoding side. What do? We throw it into our multi-head attention. We looked at that mechanism at the end. All right. And then from there, we do what's called an add and normalize step. All right. We'll look at that now in a little bit more detail. Then you get your feed forward mapping, you add and normalize again, and then you pass forward. Okay. So that's the encoder. We'll look at the little pieces there that are unfamiliar now in a second. But as you can see, the only point of our inputs of our encoder is to propagate this information forward so that it can then go in later into the decoder, right? It's not producing any outputs in its own right. All it's doing is updating the input embeddings, and then it stops. Okay. Importantly, this is done n times, so you can stack them. One thing that means is that then the output, the updated token embedding, needs to be the same dimension as the input token embedding, so that you can keep redoing the same mechanism over and over and over. Right? Hence the matrix multiplication, the linear mapping down. Okay, then second thing, the output embeddings. Now, again, we need position embeddings. It matters the order of the sentence that I'm saying, right? Again, the subject, verb, object, it's going to matter how I generate that. And so I need to keep track of those words. And then I pass that into masked multi-head attention. Okay, that's the difference there. The first layer of the decoder is now masked attention, not just multi-head attention. Why? Because I don't want to be able to see all the information that is in the future, right? I don't want to act as if I know the words I'm going to say before I say them. Okay, that then goes into your add and norm layer. We'll chat about that. And then lastly, you then pass all of that information. So coming out of your masked language modeling, your masked multi-head attention over there, as well as coming out of your encoder over there, all of that goes into another multi-head attention, okay? And this is where you now get that crosstalk. This is where you now get the ability for your decoder to use the information on your encoder side, okay? And so in this case, now your queries are going to be sitting in, and I've forgotten the order. Your queries are going to be sitting in the decoder. Your keys that you're looking for information are in the encoder, and then you propagate those values forward as normal. But what it means now is that this attention layer here is only looking back into the encoder. All right. It's only trying to now update its belief about what it should say based on the encoder. So you can break this down into pieces. This is trying to understand what it's been given, right? On the left, it's trying to understand the input text. Then here, it's trying to now embed its generated text. And then from here, it's now trying to say, how do I combine those two bits of information and look back into my encoding to now update what I should say in my decoder. Okay, from there, it is then the usual output that you've seen throughout this class. You do a bit of a feed-forward layer, and then you get your linear layer followed by your softmax. Okay, that is the standard output that we've been seeing this entire time. You've seen it in different ways, but ultimately that's that H vector that we've been talking about the whole time. Okay, softmaxing then over your dictionary size. So let's zoom in on the different pieces. Now we've done the kind of big high level thing. So looking at the encoder, that's self-attention. So the tokens look at each other. You get the queries, the key values are computed for each encoder state. Then you do the feed-forward neural network. So after taking information from other tokens, take a moment to think and then process this information. On the decoder side, again, you're doing your masked self-attention so that you don't look into the future. And then lastly, you get to your encoder-decoder attention. Now you get your target tokens looking at the source tokens. So in other words, the queries are from your decoder state. The keys and values are from your encoder states. Okay, and so that's why you also have, you will note that this is why you have the two arrows over there, because there's two bits of information coming from your encoder. It's the keys and the value. The queries are the only little bit of information now being propagated forward from the rest of your decoder. Okay, which makes sense, right? We want the information on my encoder. We want my source text to be what's driving by the values, what's driving the word that I say. Okay, this decoder embedding here, and then using it just for the queries, is me saying, is the model saying, what information should I be looking for next based on what I've already said? So again, Devin likes cats because I now needs to understand that it's just said the word because. So it needs to then know that it now needs to give an explanation. And that explanation, so it's going to then generate a query saying, I just said the word because. Please go look for explanations. It's then going to go look for keys on the encoder that say, hey, I have explanation information. Come look at me. Then when you get a high response from that, it's then going to propagate that value, which is the actual information in the encoder that you want to use to generate your next word. Okay, so that's the whole idea of the mechanism. Really, this encoder, this masked multi-head attention, is just trying to understand what it should even ask the encoder for next. Okay, and then again, your keys in your encoder is queuing that that information is present, and then the values is the information itself. Okay, following on from that, you then get a feed-forward neural network. So again, after taking information from the other tokens, take a moment to think and process and combine all this information together. Okay, this feed-forward layer, it is a little bit more kind of just generally complicated, but it's essentially just a deep neural net, right? A one-layer deep neural net. Importantly, it does have bias terms. The bias terms do play a role, but ultimately, it's just a one hidden layer with a ReLU nonlinearity, and then you propagate that forward. Okay, again, nice thing about that, fully trainable by gradient descent. All right, back propagation will tell me exactly what to do with my two layers over there. And so I don't really have to think about it. I just have to know that the ReLU has some nice properties and make sure that that information is not going to get lost as I propagate it forward. But by that point, you've done 3 rounds of self-attention, right? You've had the encoder update its belief about what it's saying based on the other tokens. So you now have this really rich semantic representation coming out of your input embeddings. Then you've now gone to your decoder side and you've understood exactly what you said, and you know the kinds of things you should go looking for next. Then you went into the final multi-head attention up here, which is between the encoder and the decoder, and you went and looked into this rich semantic information on your input, retrieved it, you knew exactly what to look for because you did a good job of attending to the decoder side. And so now you can propagate that little bit of information forward. And hopefully, if this has all worked well, and we know it does work well, you've combined all the information you need to generate the next word into quite a succinct vector representation. And that's enough for a deep neural network to work off of. Okay. One other little nuance of the architecture, and it's the thing I queued up earlier, is the fact that these attention heads are not updating the embeddings using the word itself, right? We said that when I have a focal word, all it's being used for is to generate the queries. The keys and the values were coming from the other tokens in the encoder or the decoder if we're doing the self attention, or then we just have that multi-head attention between the encoder and the decoder. But again, we were never going to be using the same vector that we were updating to update its own information. It was always based on the other tokens. Now, that in itself is not unfounded. We know about the distributional hypothesis. We've done the word to vec story. We know that we can include or understand the meaning of a word based on the surrounding words, but it would help if I didn't lose information, right? And so what we have is called a residual or a skip connection, which just literally takes the token embeddings at the start and adds them back at the end, all right? So literally you take your input token over here, all right? You do all the funny things over there that you want to do with attention. You get a new vector out, all right? And it's this vector up top here. You get this vector up top there, or whatever it is. Okay, and now you add it back to the original token you had. Okay, you add them together. That was the red one. Okay, so that seems like it could cause problems, but what's this going to do? It's going to make the red vector, the output of your attention, relative to what was already incorporated in the token embedding itself. Okay, so that red vector now is not going to be determining meaning of the word. It's doing something slightly different. It's determining the update to meaning for that word. Okay, it's the same exact idea that you get from something like a bias parameter. The green vector is your bias, right? It is what is there without more information. Okay, it's useful. It's useful to now do your regression relative to a bias than relative to 0. Okay, that is the same idea. We now update our belief about the token, all right? From here, we pass it through, so it's still there, and then all we're doing is updating that token information with the output of all of our attention layers. And you can see that they sit in all these places. You have a skip connection there, the skip connection there, there's one there, there's one there, and there's one there. Okay, so every time you're now updating a token embedding or something like that, you're going to be doing these residual connections. Okay, so that's the one thing, all right? So a little bit of a subtlety, and again, what this helps with is things like stability and precision of the architecture, and also just making sure you're not doing more work than you have to, all right? It's much, much easier to update a token embedding than it is to generate it from scratch. Okay, then we have these add and norm layers, and this is essentially just layer normalization, right? What we're going to do is we're going to take the output of all of our token embeddings, right? So you get your token at time step k, you have k minus 1, you have k plus 1, and all you're going to do is you're going to get the average of each of those tokens, the dimensions of those tokens, all right, going horizontally through them. That's a bit sloppy. All right, so you get the average for all of the dimensions of these tokens, and you also get the standard deviation of it over here, right? For the variance. Okay, and now what we're going to do, that is actually standard deviation. And so now what we're going to do is you're going to subtract the mean from it and then divide by the square root of the standard deviation for each of those dimensions individually. Okay, that is just, there's a similar thing, right? That's called batch normalization. We've seen that probably before in other courses. It's not that. It's not happening over a batch of data. It's happening over the dimensions of our tokens, all right? Of our updated tokens. But still, what this does is this means that now at least the token embedding that I have is 0 centered, so its mean is going to be 0. We know that the range of those tokens is going to sit in a nice range because I've standardized it, and so on. So now I have at least a well-behaving output token, right? Okay, and then from there, you're going to multiply it by a scale and add a bias. Those are their own parameters, right? That will also be learned from gradient descent while you're showing it data. So again, the whole point of this transformer is that you leave a lot of things up to the data and up to the learning process, right? This is saying that, okay, I can standardize it and I can zero center it, right? So I can make sure that the dimensions of my embeddings are doing something reasonably well, right? They're reasonably scaled and they're reasonably situated in my embedding space. But I don't really know if that's exactly what I want. I don't know if I want them sitting at 0, so I'm going to add a bias to it. I don't know if I want it with a standard deviation of 1, and so I'm going to add a scale to it. But at the same time, I don't want to make that a hyperparameter. That doesn't seem like it's going to be useful to me. Why don't I just make those two things just their own values and then let the data decide? Okay, and so that is a layer normalization layer. And again, it's a little bit more kind of technical than what we need to go into today. But a lot of people are thinking that the fact that you do your key times query divided by square root of dk, all right? Don't know where the transpose was. A lot of people are saying that the fact that you do this division by dk coupled with this scaling here is doing a lot of important work, right? Because this layer normalization here that happens after every time I update my embeddings is the reason why I know to scale by the division of dk. All right, I know that that's going to be an appropriate temperature to set following this layer normalization operation. Without layer normalization, that square root of dk in the softmax becomes a lot more unjustified. Okay, and so there is a lot of subtlety to this architecture that makes it very stable and able to constantly propagate information forward. You're constantly adding activity from the multi-head attention with the addition, all right, with the way you update your embeddings. And then after that, you're renormalizing, rescaling so that you can do another round of updates without having this explosion of activity or a decay of activity. Okay, so that's the whole idea of these add and norm, these layer normalization layers, is it keeps information propagating forward through multiple attention layers, right? All nk or n times of them. Okay. Everyone happy so far? No, it's a lot and it's intricate. Are we okay? Are we keeping up? Mm-hmm.
You could skip connections, just normal bias addition.
Correct. For guys online, the question was, when we do the skip connection, is that just element-wise addition? And it is. Okay. All right. The last bit of this that gets super uncomfy. And I hate this part as well. So position encodings. How do we actually represent where a word is sitting in a sentence? Right. So the problem we have is that without recurrence or a convolution, the model knows nothing about the position of the words. Again, the operation of attention is permutation invariant. Okay, so what is the solution? You need to encode position explicitly and add that into how we embed our tokens. Okay, so now there is a difference between the word cat when it is the subject and the cat when it is the object. There is a difference between the word cat when it is in the second position of our word, it's right, when it is in the second position of our sentence, or if it was first, right? This is what's going to give us, again, the ability to determine whether or not Devin loves cats or cats love Devin. Okay, so you're going to take the, you're going to encode position explicitly added back. So in the reality, the token embedding for a word is just the sum of our two embeddings. Okay, it's not, in reality, that's not kind of ideal. Again, these embedding layers should hopefully be learning semantics. And now we're confounding semantics with position. But again, if we learn this well enough, hopefully we can then start to incorporate it into a really rich semantic space so that now we get a notion of cat as object, not just cat. And we get cat as subject, not just cat, and so on. There's a lot of these, you know, the linguistics is quite deep. Okay, so then you just add them together and you get your new token embedding. Okay. So how do we actually get a position embedding? All right, so you have your semantic embedding there that we know how to get. That's just an embedding layer. You learn it. It's a linear mapping, same as word to vec. And then now we want to know, how do I represent this vector here that says I'm looking at word 0? Okay. And it's the equation at the top left over there. So the way this is going to work is you're going to represent each dimension of your embedding by a different sine wave. Okay. It's going to be like that for the first one. For the second one, let me see if I can draw this properly. It is not a good artist. It's going to be like that. All right, so it's going to have roughly the same period shifted to the right. Then the next one is going to be more like this. Okay, and the next one's going to be shifted to the right. That's deceptively difficult. Okay, and you're going to have now a sequence of sinusoids, right? So what does this mean? It means that this over here is going to be sitting at this part of my sine wave there. Okay, for the next word over here, its activity is going to be sitting at that part of the sine wave. This one over here is going to be sitting at this part of the sine wave up top there. Okay, then the next dimension is the same thing. They're going to be sitting at different levels in my sine wave. What this means, and again, there's like a bit of information theory background to all of this. It turns out that you can actually represent an arbitrary, non-arbitrary, you can represent a set number of tokens with a certain number of sine waves in these dimensions. All right, there's like a scaling to it. Okay, and so that's the foundational idea of it, is I'm going to then, because each of these dimensions have a different period and a different offset, there will be clashes, right, on a single dimension. There will be this habit of it going up on that token, down on that token, back up on that one, right? Now, in the first dimension, I can't disambiguate that value from that value. They're both on the up of that first sinusoid. But if I have enough different frequencies, all represented down the vector, you can prove that they will never clash. In other words, you will get a unique vector representation for every single place in my sentence, again, up to a certain length where your period kind of, all of them go back into phase and reset. In which case, if you run into that problem, you just need to add more of these functions. You need to add more dimensions to your position embedding. Okay, so let's look at how this works. So firstly, let's see if there's a nicer way of doing this. There's not. Okay, so firstly, we're going to use, for all of the dimensions that are even, all right, so for our I dimensions, you're going to use a sine function, okay? For our odd dimensions, you're going to use a cos function. That just gives you that 90-degree offset, okay? So that's the first thing. Secondly, you take your position. That is the value. That's 0, that's 1, that's 2, that's over there. You feed that in, you divide it by 10,000, and then you raise it to the power of 2 times I, so 2 times the depth of the vector that you're looking at, okay? So this is now what gives the different frequency to all of the different dimensions of my position embedding, is the fact that now you're raising it to a power depending on how low down this goes, okay? Depending on how low down this goes. So now because I is larger over here than it was there, you're going to have that cycle through your sine being a lot quicker, okay? And then lastly, you divide by d, the dimension of your model. And this is what makes sure that the dimension of your token embeddings, you have enough sinusoids to get you to represent all possible positions, but admittedly no more. Okay, so this is what determines the number of these sinusoids you need to represent all of the positions uniquely. All right, and that is it. There's a few pieces to it. The fact that you use 2 different functions for the odds and even indices over here is always a little bit tricky to me, but it's the same kind of foundational idea. All right, depending on the position I'm at, will tell me where I am in a particular sine function, and depending on which dimension of my embedding I'm caring about, gives me the different frequency. So this has a higher frequency than that one, for example. Okay. Does that make a bit of intuitive sense? I think we can linger here if we need to. But do we understand the idea of this? If not, the formal proof that it will represent all places. Guys online, are we happy? I notice we've lost 3 people in the last 10 minutes, but like 7 people across the lecture. There's something going on today? Are you guys all right? Just tired? Or are you angry at me for my test? Is that it? Am I getting silent treatment? Guys, are you angry at me? What is
no, but are you supposed to be filming? Because I think the camera's on and that might affect the recording.
Wait, what? The camera's on?
Yeah, I can see, I think that's the roof of the class.
Huh, interesting. I hope that doesn't affect the recording, but I'm sorry you've had to stare at my forehead for the last like 20 minutes. Damn, why? It's not even letting me not do that. All right, I'm going to stop for 2 seconds. That's awkward. All right, you can see the screen now and not my face. Correct? Cool. Damn, that's going to be an unflattering video to edit later if I have to. Okay, are we kind of comfy with these ideas? Yeah.
I'm going to add another day.
I mean, one wouldn't be enough, probably. That'd be a lot of information to squeeze into one. But if you, like a BERT model, you learn it. So it is, you're correct, it's learnable. At the time this was published, I guess they felt that all that was needed was something that explicitly represented the index differently in a vector way. So they went with that option. But yeah, now, particularly as you get to arbitrary length input sequences, this fails, right? Or you have to get really large to accommodate everything. And so in that case, then it became a learned thing that they do start learning now. So you're correct. Okay. Let's wrap up the last 15 minutes here. So that's our architecture. Then usually this class goes into BPE, but we did that earlier. So how do we now try and understand what's going on in these networks, right? There's a lot of moving parts. There's a lot of different behaviors. So people have been kind of caring a lot about how do you understand what a transform is doing. So there's a few. So number one, there's model-specific methods. So you can look at certain components of the model. All right, and so you did see versions of this in previous lectures, right? The ideas are the same, the architecture and the mechanisms are different. But again, there's nothing about transformers that are completely unfamiliar to kind of machine learning and stuff. Like most of these ideas are still grounded in like, the last 20 years. And so in previous lectures, or 40 years, so in the last lectures, you saw the fact that we can interpret convolutional filters, for example. You went and saw what made which part of the image was most responsive to a particular filter, for example. Which filter was the one that enforced my classifier the most, right? You could then try and interpret different neurons within your RNN or your CNN, right? You could ablate certain neurons, but you could cut out certain convolutional filters and see how that affected the output of the model, all right? So that's the same kind of ideas there. And then today, obviously, what people really care about is looking at what these multi-head attentions are doing. Okay, on the model agnostic side, you know that you can take representations from one model and try and understand what it's doing by using them to predict other things. So for example, we never explicitly taught our language models parts of speech. We never explicitly taught them grammar, but we then can go and try and look at, can it predict parts of speech of words? Is that something that our embedding of these words implicitly encoded just because that was something that was useful to performing the original task of generating language? Okay, and so if you want to understand if something is present in an embedding, the answer is to try and decode that thing from the embedding, or at least that's one really common way of doing it. Okay, and so what do we do today? Well, we probe and you try and see what do the representations of these transformers capture in almost exactly the same way. Let's look at how you look at multi-head attentions. So you want to say, what are these heads doing? So heads which on average contribute more to generate translations are called the important heads, and they tend to play interpretable roles, at least if you look at these papers and stuff like that. And it turns out that indeed they actually do collapse to very, very reasonable things. So for example, some attention heads just genuinely look at what position a word is in a sentence, and that's all it does. Others look for particular syntaxes. Others look for rare tokens or rare words. And in that case, those are generally used for things like retrieving names from the context, right? When ChatGPT suddenly uses a word that you used a whole bunch earlier, it turns out that it's realized that what is needed is a name or a rare word, and it just went and found those in its context and copied it out. Okay, and so for example, here you can look at the how much attention is placed between words. So this is literally the attention weights for every single word compared to every other single word in your input, mapped onto just a matrix. And you can see in this case that, for example, the word have is looking one token to the right. Okay, they're looking up to the next token in the sequence, all right? Or a lot of them are then looking one token back. I always have to remind myself which way this goes. Yeah, EOS. Okay, so this is on the input side. This is what it's looking to. All right. So this is, if I remember correctly, this is your query. This is your key. Okay. And so when I'm querying for the word have, you're looking in your encoder to what you might have. You're looking one word forward, and in this case, the EOS can't look one forward, so it just stops. But there is the else one word tokens that are looking one word back in the sequence. This is something obviously that's a lot more common in something like a decoder, where you need to keep track of what you've already said, what word came just before. This, when you couple it with depth, so what did I just say? I find the word before this, and then is the value coming out of that word. What does that value tell me? Well, that value tells me it was a subject, it's a noun. And so that means I must now generate a verb for this to be grammatically correct. And that's very much how these attention maps start to work when you start putting them together, both in parallel and in depth, right? Because now I have a mechanism to go and look back. The next layer might find a mechanism to go and look one step forward and copy. Okay, and they all do these very similar things. And again, the most famous one is called an induction head, which does just that. All right, and this is where the induction head is where you can do things like show it logic operations, and then it learns how to copy the logic operator out for new examples. Okay, same story here. You can see verb subject matching. So in this case, when you're trying to understand the word heard on the right hand side, on the left hand side here, I'm trying to process the word heard here. So what am I going to do? I'm going to look at who is being heard. All right, who am I speaking to? You might have heard. So now it goes and looks back to that. All right, same thing here when it says we're starting. What is starting to happen? You're starting to lose. So you then place a little bit of attention over there. Sorry, when I'm processing the word may, it's putting value on the word that, right? That only makes me. So now I can start to do this kind of verb subject mapping over there. If it was verb object mapping, then we would look at me instead. And so they tend to be relatively interpretable. And in these cases, what also often happens is that they collapse onto something like an identity matrix or a very little bit of information where it's not needed. But the problem with these is that they are very seldom completely clean. So you can see a lot of muck going around over there where the attention is still a little bit diffuse. And that is by design. Obviously, we're now giving a temperature parameter that stops the softmax from always collapsing onto one word, unless it's obvious. But again, now that means that there's always a little bit of irrelevant or unnecessary information propagating forward. But hopefully that last W0 matrix Can you still hear me? I dropped for a second. Cool. All right, the same thing was found. There's subject to verb tracking. So that makes and you heard. So again, you're trying to see what someone might be doing. Object to verb mappings. You can go through these and have a look. There tends to be, there's quite a lot of them. Again, this paper went quite deep. And then in general, you also get rare token heads, which are always looking at or always attending to these really strange tokens in our sentence. Why is that helpful? Well, because rare tokens are almost always meaningful, right? So if we're talking about the terminology indications of source and appellations of origin, that word appellations is really rare. We don't really know what it is. And so now we're going to look back and always try and disambiguate it as our model moves forward. Okay, same thing here. It's looking at the word Virginia. Why does it always want to attend to Virginia? Well, maybe that tells me about something to do with the governor. Maybe that helps me talk about when I'm trying to understand what West is. Is it West Africa? Is it West in the world? Or is it West Virginia? And so we look at the word Virginia. The governor is unique in that case, all right? Maybe they announce certain things in a specific way in Virginia. And so you will always be looking at those rare tokens to try and use that as a very key bit of information. Okay, and the same bit for names and things like the word fabulous and so on. Okay, so that's the first thing. And again, that's a really easy way to do this analysis. And you usually do it on like your first few layers of your neural network. In fact, if you do it on your first layer, you usually get to the cleanest representations. If you do it later on, you get quite rich, diffuse attention. Okay, then you can also try and predict what do representations mean. So we've seen this before. So how do you understand if a model captures linguistic properties? Well, firstly, you can just take your pre-trained model and you get the representations from some layer in your neural network, right? It can be the output of our multi-head attention model at any depth we want. You just go and take those representations, and now you see, can I label that token embedding for Can you hear me again?
Okay, now we can hear you.
Yes, sir.
Sorry about that. That's Wi-Fi just dropped. Cool. All right, let's wrap this up. I know we're right on time. Okay, so we were chatting about how do you know what it's doing. You take an embedding of a word coming from some layer in your language model, and then you try and see, can you predict the partial speech from it? And again, the only way that you can do that is if that information is somehow contained in the bit embeddings themselves. Okay, so if it can learn that, if it gets low loss, and if it seems to generalize well from that, then you can say, or at least start to make claims that that information is represented in an embedding space. And that's called a probing classifier. Okay, and so for example, in neural machine translation models, you can say try and kind of probe morphology. So in this case, you can take different NMT models for different language pairs and look at the different decoder and encoder layers and see how they perform when you try and predict kind of different morphological features from them, right? So for example, if we're translating from French to English in this last one here, second last one there, it turns out that in that case, you can predict a lot of morphological features coming out of the different layers of that language model, right? Of that translation model. In general, though, and across this entire trend, what they found was that layer 1 tends to be better at representing morphology than the later layers. So clearly what that means is that there is this kind of point in the network where it's using morphology to update its information, but for the actual task itself, it's an intermediary kind of step. Okay, and then there's obviously different levels of accuracy on this, meaning that different neural machine translation models perform better or worse at different morphology mappings. Okay, so encoding helps, layer 0 words are the worst, and so you get some benefit from doing the attention updates and so on. Okay, similarly, you can make them predict parts of speech. So again, in this case, if you just have a normal language model where you look with the same source language and different target languages, you can compare those. So in this case, we're looking at different target languages, which is Arabic and English, and I don't know what the other two are, but probably translating from French. And in this case, you can then say, well, it turns out when we're doing translation from French into English, we get the best parts of speech representation. You get slightly better morphology. It turns out that probably something like Arabic is the worst for those same parts of speech mappings. And that's likely got something to do with the fact that the family of languages those are coming from and their origins are slightly more distinct. Those languages evolved in different areas and to behave slightly differently. Okay, so it's surprising. Weaker target morphology leads to a stronger encoder. All right, so that was the one other weird thing they found. And that's it. All right, so I know that's a lot of information at the end, but as long as you understand the main mechanisms of the transformer, that's the point of today's lecture. And if there are any questions for that, we have 2 minutes to wrap that up now. We good? We all understand transformers now? You can go code it up for your project. All right. If you let me know which part of that is the part that you don't like, so like the position embeddings is a common one, obviously. But if you tell me what part of that to focus on, I can then focus on that going forward because we don't now stick around on transformers for a while. And so those ideas will set in more, but it helps if I know where you guys are feeling uncomfortable. You don't have to tell me now, but if you do get an idea during the week of where Devin should focus, you can let me know. Cool. Thanks, guys. I'll see you next week. How you doing, mate? Yeah, what's up? All right, stop recording. Yeah, what was the question?